So the next law, and a very important law in circuit analysis, is the Kirchoff's voltage law, or more commonly known as KVL. This states by definition that the algebraic sum of voltages around a closed path is always zero. A closed path is basically a loop. I'll just show an example that if this is a circuit and there's a battery connected of 2 volts, and because this is clearly a closed path or a loop, the voltage across this element would also be 2 volt, the same as this. Now in another example, a little more complex example, I'll show how the algebraic sum works. Now if this is a circuit we have and I need to find the voltage across this 2 ohm resistor, and I'll just apply the KVL to find the voltage. Now as by definition the algebraic sum of voltages around the loop should be zero, so we need to find a way to find the algebraic sum in the first place. The easiest way to do that is just take a node, just take a point. I'll just take this point. Now start moving clockwise in the circuit, and whenever you encounter a negative element, a negative sign first, write a minus, and whenever you find a positive sign first, just write a plus. Now for resistors, whenever you are moving alongside this clockwise path, whenever you enter a resistor, because this is the direction of the current you are following, so just because the current enters the resistor always from the positive side, so this would be the voltage, because voltage always has polarity. So we can just apply the KVL. Starting from here, we'll just move clockwise. Here in this battery, I encountered the positive sign first, so I write -2. Then I encounter the negative sign first again, so I write -3. And then I encounter the positive sign, so I write plus V. And then I reach back at this point, so this is equal to 0. And if I solve this, V is clearly 5 volt. Now I'll show another example to make things more clear. Now we are given two voltages here, the voltage across this element which is 4 volts and the voltage across this battery which is 8 volts, and I need to find the voltage across R. The first thing about voltage, it always has polarities. So as I said in the previous example, we'll just start off from any point. We'll just start off from this point, and everything we encounter, and we'll just write off the signs. So here I encounter the positive sign, so I write +4. Then I encounter the positive sign first again, so I write +8. For the resistor, as I'm moving in the clockwise direction, this would be the polarity. I'll always encounter the positive sign first, so I will write just +V. This is equal to 0. So by solving, V comes out to be -12 volts. So this is how you apply the Kirchhoff's voltage law. Now to make things more clear, how the backing behind the Kirchhoff's voltage law is the law of conservation of energy. Voltage is the energy that every charge has. So if you're moving around a loop and a charge comes back to its original position, here the charge has zero energy because it has spent all its energy around the loop. That would mean that it would always use all of its entire energy across each element, so that it comes out to be zero, and this is why there's a zero here. So this is how the Kirchhoff's voltage law works. Now, in this last example, we need to find this voltage between these 2 points, because even though there is no wire here, there is no element here, but still the voltage or the potential difference is basically the difference in the voltages between 2 points. So this can be possible. So we'll just apply the KVL. We'll start off from here. So the first sign I encounter is +8. Then I move on to the next element, and the first sign I encounter is +2. And then when I come here, I can just go here, and it would be +V, because I've jumped the whole potential difference, and then I'm back at this point. So I'll just equate this equal to 0, and V comes out to be -10 volt. So if I connect an element here to measure the difference of potential between these 2 points, I would always find -10 volts. So this is how the Kirchhoff's voltage law works, and I hope this is more clear.